So dear students, the topic for today will be potential energy of a dipole in an external electric field. So we are going to calculate the potential energy of a dipole in an external electric field. Okay, let us draw electric field lines directed towards this direction. So this is our uniform electric field. This is our uniform electric field. And let us take there is a dipole this way, minus q plus q separated by a 2a distance. So all we want here is to calculate the value of the potential energy of this electric dipole in this electric field. So what will be the potential energy of this dipole in this electric field? So for that, I want to make a consideration, and the consideration is, so consideration, there is one consideration. Actually, this is not a consideration, but it has an explanation behind it, but I'm taking this as a consideration because there is no time, or it is very difficult to explain these things in videos. So let us assume, or let us consider, if a dipole make 90 degree, if this dipole make 90 degree with this electric field lines, if this dipole makes 90 degree with this electric field lines, then potential energy in that case will be 0 for the dipole. Simply, potential energy of the dipole will be 0 for that case. Okay, so using that consideration, so we are going to derive the potential energy of electric dipole. So this is your uniform electric field. So this is your uniform electric field. And so it is making 90 degree with the electric field initially. Now what you are going to do is you are going to rotate it. You are going to rotate it. Let us take, you are going to rotate it by an angle of, let us take theta, or let us take by an angle of d theta. You are rotating it by an angle of d theta or delta theta, and you have made a new orientation. So initially your dipole was in this position. You rotated by an external force, and it oriented in this direction, or it got displaced by an amount of d theta. So here displacement or angular displacement is your angular displacement is d theta. You have displaced the dipole by an angle of d theta, and while rotating you have utilized a torque. Instead of force in rotation, we utilize torque to rotate things. So to rotate this particular dipole, you have utilized an external torque. So in this case, the external torque will be external will be simply, we know from our previous derivations, torque experienced by a dipole in an electric field is nothing but it is P cross C, that is dipole moment into it is a cross product between dipole moment vector and electric field vector, which is simply equals to, in magnitude, Pe sine theta. So you have an external torque, you have an angular displacement. So work done in rotating this particular dipole by an angle of d theta will be, work done in rotating the dipole will be your, work done in this case will be your tau external d theta, that is force dot displacement. So force in case of force rotational motion, there is a torque, and in case of linear displacement, there is an angular displacement. So work done is force into displacement, and you have displaced it by an angle. Okay, initially let us take its initial position was theta I, and finally it got displaced to theta f. So initially it was at theta I and it got displaced to final angular position, that is theta f. So you have displaced this particular uh, dipole from initial theta I configuration to final theta f configuration. So work done in that case will be theta I to theta f. Tau external is here nothing, Pe sine theta d theta. Now Pe is a constant in this case, so Pe comes outside. So theta I to theta f sine theta d theta. Now integration of sine theta d theta is minus cos theta, or it is okay minus cos theta. So work done is Pe minus cos theta from theta I to theta f. So negative sign take outside, so Pe cos theta from theta I to theta f, or work done is minus Pe cos of, this is from theta f to cos of theta I. Now we already know that our initial theta I was 90 degrees, because in this case our potential energy was 0. This was our consideration. So theta is equals to 90 degrees. So work done will be minus P into E cos of theta F minus cos of 90 degree. So that will give me minus PE cos theta F minus 0. Cos 90 is 0. So your work done is minus PE cos theta F. So this can also be written as dot product between P and E. So W is equal to minus P dot E. So P dot E is P cos theta. So this is the work done in rotating this dipole in an electric field from theta I to theta F, and this work will be restored as the potential energy of the dipole. Therefore, potential energy of the dipole will be U will be minus P dot D. So this was for today. Thank you.